Section 1.5 is writing numbers in scientific notation, but before we get to scientific notation, we must know what standard notation is. And standard notation is defined as the normal way that people write numbers. For example, we can just say 1 or 10 or 100 or 1,000 or 1,000,000, and we would write those in this standard way as shown here. But these types of notations don't always work in the sciences because we often deal with numbers that are really huge or really small. So for example, we have 1 mole of a substance is 602 hextillion 200 quintillion particles. And that looks like this in standard notation. 602 hextillion, 200 quintillion, and then the rest are zeros. There's quadrillion, trillion, billion, million, thousands, and then the ones place. There are 3, 6, 9, 12, 15, 18, 20 zeros in that number. That's very tedious to write and seemingly unnecessary. So instead, we could write that in scientific notation, and it could be 6.022 times 10 to the 23rd. It takes up a lot less space, and you have the same information conveyed in here. In this, the number 23 right there, which is a power, 10 to the power of 23, tells you how many times you would need to move the decimal place, which would be right here, to the left to be before the 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and 23 times. And then you have the 6.022 portion right here in there. Scientific notation always has a number followed by a decimal, and then the rest of the number after that, and then times 10 to some power. You will always have that in every scientific notation. It saves space, it saves time, and for especially large or especially small numbers. Another example of a number that would really need to be in scientific notation could be the size of a hydrogen atom, which is listed as a radius of hydrogen equaling 0.00000000053 meters. Now if we count those all up, because that's a lot, I hopefully got it right. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros in this. That's how many times do I have to move the decimal place? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. So in scientific notation, the radius of a hydrogen atom is 5.3 times 10 and to the power of negative 11 meters. When the number is between 0 and 1, meaning it's less than 1 but bigger than 0, you have negative exponents there. The 11 still tells you how many times the decimal place has to move from standard notation to scientific notation. It moves 11 times. The other probably easier way that I would look at scientific notation from these standard numbers would be to count the number of zeros here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 of them, which is the same number there. The decimal place moves the same number, 11. The exponent here is 11, And so it all works out the same each time. All right. Now, tables 1.2 and 1.3 on pages 17 and 18 have some information about scientific notation. And you can see those here. Table 1.2 says some powers of 10. So over here on the far top left, it has 10,000. They don't use commas in this book, apparently, but that would be 10,000. And 10,000 is really 10 times 10 times 10 times 10. And you can see in there, there are 1, 2, 3, 4 zeros. And in the number 10,000, there are 4 zeros. So what we get in scientific notation is 1 times 10 to the 4th, because it's 10 multiplied by itself 4 times. For the number 1,000, you can see right there, it's 10 times 10 times 10. 3 zeros total here and here. Since it's 10 multiplying by itself 3 times, you get 10 to the 3rd power. And so on and so forth. Now, if you have 0.1 in standard notation, that's the same as 1 divided by 10, or 10 to the negative 1st power. This number here has 2 zeros in it, before and after the decimal. It's 1/10 times 1/10, or 1/100th, which is 1 times 10 to the negative 2nd power. Table 1.3 says some measurements written as standard numbers and in scientific notation. And so the volume of gasoline used in the United States each year, which is a crazy amount, 550,000,000,000,000 liters. That's 5.5 times 10 to the 11th liters. Much easier to see that. In standard vernacular, that would be 5.5, so it would be times 10 to the 11th would be 550 billion liters every year. And if you divide that number by the approximate population of the United States of 330 million, that comes out to about 1,600 or to 1,700 liters every year per person, which is a lot of gasoline. The diameter of the Earth is 12,800,000 meters, or 1.8 times 10 to the 7th meters. And you guys can read the rest of those and just see, well, I'll do the last one here. Mass of a bacterium, a mycoplasma bacterium has 0.00000000000000000000001 kilograms, which is 1 times 10 to the negative 19th kilograms. Obviously, that number is just way too small to actually look at and understand. This is a heck of a lot easier. So that would be 1 times 10 to the negative 19th kilograms. That's 1 quintillionth of a kilogram. I'm sorry, it's 100 hextillionths of a kilogram. You can't even fathom how tiny that is. So the numbers are obviously best represented, at least in my opinion, and most of the scientific community's opinion, in scientific notation. It also makes it a heck of a lot easier to type them into your calculator if you're using numbers like this in your calculator. Sample 1.8 on page 18 says to write each of the following in scientific notation. You have 3,500 for part A here. I'm just going to rewrite that. All you need to do in order to convert that number into scientific notation is to make the imaginary decimal place right there and then move it until it's before the first number. In this case, we have to move it to the left. How many times do we have to move it to the left? Just count. 1, 2, 3. So it moves 3 times to the left. which means that 3,500 equals 3.5 times 10 to the third. Since that's a 3, that's a 3. Question B, whoops, has 0.000016. There are 5 zeros. You can just count them up. 1, 2, 3, 4, 5. So you could simply jump from there to being 1.6 times 10 to the negative fifth. Or you could count how many times you have to move the decimal. 1, 2, 3, 4, 5. So it moved 5 times to the right, making the answer 10 to the negative fifth. Practice problem 1.25. Write each of the following in scientific notation. So let me zoom out a little bit. Hopefully you can see this, but we've got part A here is 55,000. And I'm going to write that in scientific notation. So again, how many times do I have to move the decimal place to be after the first number? 1, 2, 3, 4 times. So this comes out to 5.5 times 10 to the fourth. Part B here is 480. And so how many times do we have to move the decimal? We put it in there after the last number, and then 1, 2 times. So 4.8 times 10 to the second. Problem C here, 0.000005. I believe there were 6 zeros. Let's count them. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so we got that right. Since there are 6 zeros, this becomes 5 times 10 to the negative sixth. Problem D here is 0.00014. There's a total of 4 zeros. So this is equal to 1.4 times 10 to the negative fourth. Problem E is 0.0072. It has 3 zeros. So 7.2 times 10 to the negative third. And problem F, 670,000. All right, so if we have the decimal place right here, move it 1, 2, 3, 4, 5 times. 6.7 times 10 to the positive fifth. And you might be asking yourself, well, okay, so what happened to all the zeros? There's 3 zeros here. There's a 0 here. And I'm saying after the last non-zero number. And we've got 4 zeros right there. What happened to those? Well, in this class, when we're doing things in scientific notation, we have to think about significant figures. And it turns out that with no other context with the numbers, zeros are not significant. So I'm going to always ignore these rightmost zeros when I write them in scientific notation. Now, in problem C, D, E, and F, or C, D, and E, there are no rightmost zeros. So it doesn't matter. We just write 5 or 1.4 or 7.2. But for the other ones, since there were, they're not, and the numbers are bigger than 0, those zeros themselves I should say, since these three are bigger than 1, not 0, these three are bigger than 1, the rightmost zeros are insignificant, so you don't write them in the scientific notations. Okay, here we're on practice problem 127, which says which number in each of the following pairs is larger. When we have example A here, we're comparing 7.2 times 10 to the third and 8.2 times 10 to the second. Now if you simply just look at the numbers in front, what we call the coefficients, you see 8.2 and 7.2. And you might say, well, 8.2 is bigger than 7.2, and so you would choose that. But you would be wrong in this case, because what you really are supposed to do is look at the exponents. And so out of these two numbers, if you look at the exponents, you'll see 10 to the second and 10 to the third. 10 to the third represents 1,000 and 10 to the second represents 100. So you really get 7,200 versus 820. So let me show you that here. 7.2 times 10 to the third. If you're trying to put that in standard notation to make sense of this, what you have to do is the opposite of what we just did. And that means move the decimal place to the right. So I'm going to write 7.2, and I'm going to move that decimal place 3 times to the right. 1, 2, 3. Since there are 2 empty spaces there and there, you put zeros in for them. And so this is 7,200, and you can put your decimal right there. 8.2 times 10 to the second is going to be 8.2. I'm going to move the decimal place 2 times. 1, 2. We've got 1 empty space right there, so we get a 0, and that's 820. Now when you're comparing those two numbers now, you see 7,200 versus 820, and the obvious answer is 7,200. Now, if we're doing problem B, we have 4.5 times 10 to the negative fourth versus 3.2 times 10 to the negative second. Okay, so again, the real first thing you should do is look at the exponents. We have 10 to the negative second and 10 to the negative fourth. Which is bigger? You might say 10 to the negative fourth is bigger because it's a 4 versus a 2, but you'd be wrong. 10 to the negative fourth is actually smaller. That's 1/10,000th of something, whereas 10 to the negative second is 1/100th of something. So do the same thing here. We're going to move the decimal in the opposite direction to go to standard notation. So for this, we have 4.5. I'm going to move it 4 times to the left. 1, 2, 3, 4. We've got 1, 2, 3 empty spaces. So you would write those zeros in. 1, 2, 3, and then 4, 5. Your decimal goes here, and then you would write the 0 to the left. How many zeros are there? 1, 2, 3, and 4 of them. Do the same thing for that 3.2 times 10 to the negative second. Move the decimal place 2 times to the left. 1, 2. We've got 1 empty space, so this becomes 0.032. Now out of those, which one is bigger? I think it's fairly obvious that the 0.0045 is smaller and the 0.032 is bigger. So the answer is 0.032. Okay, example C says 1 times 10 to the fourth versus 1 times 10 to the negative fourth. 1 times 10 to the fourth is 10,000, you got 4 zeros. And 1 times 10 to the negative 4th is also going to have zeros, 4 of them, but they're going to be before the 1. So your obvious answer is 10,000 is larger. 1 times 10 to the 4th. For problem D here, 0.00052 or 6.8 times 10 to the negative second. There's many ways you could do this. You could convert the 0.0052 into scientific notation, and I'll do that for you. There are 1, 2, 3, 4 zeros, so 5.2 times 10 to the negative 4th. And then you could compare the exponents, negative 4, negative 2, and so that number is bigger, 6.8 times 10 to the negative second. Or you could convert the 6.8 into standard notation, and you have 6.8, move it to the left 2 times. You've got 1 empty space, so you've got a 0 there, 0.068. Compare that to this number here. Since this has fewer zeros, that is your bigger value. So out of all of these, the bigger ones, you've got 6.8 times 10 to the negative second, 1 times 10 to the 4th, 3.2 times 10 to the negative second, and 7.2 times 10 to the 3rd. So in summary, we learned what chemicals are. We learned the definition of chemistry. We learned what conclusions are, experiments, hypotheses, observations, the scientific method, scientific notation, and theories. And we obviously also went into some introduction into some mathematics. But these are the key terms listed at the end of the chapter in your book. The problems that I would like you to do in your book are listed here: 31, 43, 45, 47, 49, 53, and 55. And those are on pages 23 through 24. I will be posting some mandatory homework problems on Blackboard, not these ones, because the answers are in the book. So these are just practice problems you don't have to do, but you should do, in my opinion. It always helps to do more. And you really will need to practice doing the mathematics if you want to pass this class. So work on those problems and look on Blackboard for assigned problems that you have to do in order to get your homework grade. And I'll post those the same day that this video posts.